So the encoding concept is nothing but when you send the data from one device to another device, so it's carrying like a signal, right? So the encoding is just encrypt the data for the security purpose. So what are the types of encoding? And the receiver side, it automatically decoding the corresponding data, right? So the encoding means here is a NRZ concept and NRZ I and Manchester and 4B and 5B. So these are the types. Before that, we should understand the encoding concepts, right? So we will see one by one. First, see this diagram here, the line encoding and decoding method. This is called the line encoding. So what happened in the line encoding? So in the sender send the data here, the corresponding sender send the data. That entire data will be converted into the digital data, whatever it is. If you send a good morning message to your friend, that GOOD, that good morning, that will be converted into binary format. That will be converted into binary format and sent to the transmission medium like a signal, and the receiver side, that binary format is reverse, that is a decoding and a display to good morning to your friend. So you couldn't see the conversion values, right? You just you can see only the corresponding the text or actual string, right? So that conversion is called the here the encoding method. So the binary data will be encoded and sent to the receiver side. That is called the line encoding and decoding method. So see this diagram here. Yeah, this is a digital data. So the corresponding data will be convert 0 1 0 1 like that 1 0 1. The same data will be encoded here and sent to the digital data or digital signal and reach to the destination or the decoder. The decoder, what happened in the decoder side, it automatically decode the binary data or the digital data to the original data. So this is called line encoding and decoding method. Okay. So the line encoding means is nothing but the converting a signal. Already I told that good morning message will be converted into zeros and ones. That is called the digital data. So into a sequence of the signal that denote ones and zero. So the entire message will be converted into zeros and ones and sent to the signal, the sequence of signals, right? For example, sir, how can we understand the ones and zero will be the text format? Here, the high voltage is indicate plus V, right? High voltage. Or otherwise, it is represent 1. On or off. We will take another example. On or off. If on means the value will be 1. Off means the value will be 0. So that 1 and 0 denote some information. It hold some information, right? So that's why that entire message or the encoding method, the data will be converted into binary. And the binary, okay sir, how it is encoding and through the signal, the original binary data is converted into signal. That is the encoding method, right? So what happens inside, see this diagram here. This is a 0 and 1 and 0 1 1 1 again 0 1. So this is a binary or the digital data. So this data will be converted into signal. So how can I represent that signal? So 0 means that is a base. There is a no wavelength. So 0 means here I indicate this is a 0. This line is 0. The bottom of the 0 line, right? So this is a 0. And if it is 1 means it is a shape of ones. That is the rise and this is a shape of 1. So this full line is calculated as 1. What is the next value? Here 0. Here 0. Again the bottom line. This is a 0. Then again 1 1 1. So there continuously 3 1 is here. So what happened? I'm just draw the signal here 1 1 1 1. So 3 1. Again it will be 0. So this is a 0 and 1. So the digital data is converted into signal. This is called the line coding method. The digital data is converted into the signal. So this is called the line coding method. Now you can understand how the binary value will be converted into signal. Okay. So in the receiver side, the same signal is converted into binary and the binary converted into original message. So this is the process, right? The signal is a digital signal is converted into digital data and the digital data is converted into original message. This is a line coding method. And here the encoding terminologies. So what are the encoding terminologies here? So the encoding terminology means first one is the data element and the signal element. This is a data element, this is a signal element. This is a data element, this is a signal element. So these are the another the encoding terminologies. So the small entity that can represent the piece of the information already told. 1 means on, 0 means that is off. Some piece of the information hold in the digital, the data element. And the signal element means here the corresponding signal element carry the data elements. Yes, of course, because the corresponding data only is converted into signal. So the signal is also carries the data element. That is also a piece of the information called, right? And the next point, the data element are being carried and the signal elements are carriers. So these are the carried with the piece of information. That information is carriers by the signal element. Next, one of the main terminology is denoted ratio. That is R. The ratio R. So what is ratio R? Actually, the ratio R is which is the number of data elements carried by the each signal element. Again, I repeat. Ratio R, which is the number of data element, zeros and ones, number of data elements carried by the each signal element. So the carried element, the data element is 101. The signal element is 1. So this is called the ratio 3:1 or 1:3, like that. So the ratio of the data element and the signal element is called the ratio, right? R, that is denoted as R. So we will see with one example. Yeah, this explanation here. First one. First, see the first diagram. Here, one data element per one signal element. So the corresponding ratio is 1. One data element and the per one signal element. So the corresponding ratio equal to 1. So how can I draw the diagram by this data element and the signal element? So this is a baseline and I denoted this is the space of the signal. Here, this is a space. This is a space. So this is a data. This is a signal. This is a one signal, second signal, third signal. So 3 signal is here. Per signal, I denoted only one data. So only the one data elements per one signal element. So the ratio is 1. You just calculate the distance, right? So this is a single. Sorry, it is a signal, one signal element, right? Okay, come to the next diagram here. The same space is here, but it is divided into 2. Divided into 2. But the element, the data element is 1. So what is that is a ratio here? One data element here. This is a one data element per 2 signal elements. This is a 2 signal element, right? So within the space, there is a 2 signal element is passed, but it is denoted as only one data element. So the corresponding ratio equal to 1/2. 1/2. Okay. Come to the next, the C diagram. 2 data element per 1 signal element. 2 data element, 1, 1. The same space is a single signal, but the data element is 2. So the corresponding ratio equal to 2. So always you remember you have to denote the data number of data elements is a value of R. If the element is 1 means here 1. But here R value equal to 1 by 2 because you have to split the corresponding signal. So that's why the signal is 1 by 2. Okay. So here the two data elements is entered in the single signal element. So the value of 1 1 equal to 2 data element, the ratio equal to 2. So here see the lost diagram. The 4 data element is denoted as here like this. That is a 3 signal elements. 4 data elements. 4 completely. The 4 data elements is per the 3 signal elements. So 4 by 3. Here this is a 4 by 3 value. So the corresponding R value is equal to 4. So the always 4 is denoted the data divided by this is a signal. This so the formula is data divided by signal. Here 1 by 1, here 1 by 2, here 2 by 1, here 2 by 1, here 4 by 3. 4 by 3. Now you can calculate the signal element as well as the data element. So this is a very basic structure of the signal element and data element to understand the concept. Okay. So see here. Here the signal rate versus the data rate, how it is calculated, the corresponding unit, right? So the data rate is always represent the bits. So how many bits can send in the 1 second? That is the BPS, bit per second. So only the data rate, the net speed and the broadband speed, fibernet speed, that is calculated by the data rate. 5 Mbps, kmbps, so 100 Mbps, 500 Mbps. These are the data rate, the speed of the network or the internet. So that is denoted as bits per second. Now it is available 1 Gbps per second. That is a ultra speed here. If you are using the well connected the fiber cable, you can transfer the data 1 Gbps. That is a 1 gigabyte per second. That is extreme speed. In the same way, the signal rate is also is calculated by 1 second. Pulse. That is a pulse. Pulse per second. Pulse per, there is a PPS, pulse per second, PP, double PS or Baud. So this is a unit is Baud. So one goal of the data communication is to increase the data rate here, increase the data rate, speed of the transmission, that is denoted as the speed of the transmission, increase the data rate and decreasing the signal rate, the bandwidth requirements. So this is a goal of data communication. When you increase the data rate, it will be the speed of the transmission will be increased. If the signal rate is low, you can easily transmit the data. That for example, here you can transmit the 4 data element per single signal, means you can transmit more element or more data element in the signal. So the bandwidth requirements is like that, decreasing the signal rate. So this is the goal of data communication, right? Okay, we will calculate by the some formula here, the data rate versus baud rate, that is signal rate. So the worst case is maximum signal rate. Maximum signal rate. The best case is minimum signal rate. The best case is minimum signal rate. For the average cases, here the formula for used here, S equal to C into N into 1 divided by R bars. So S equal to here, see here, already I told when the data communication, the corresponding data rate is increasing, that is the speed of transmission increasing while the decreasing the signal rate. So we have to calculate the formula by this S equal to C into N into 1 by R. Already we have discussed what is how to calculate the R value by this diagram, right? We can calculate the R value 1 by 2, 3, 4 by 3 based on the data element and the signal element. In the same way, we have to calculate the C value and the N value, capital N value. So whereas the N is the data rate, here the corresponding N is the data rate. And C is the case factor, that is either it's maybe worst or best or the average. Okay, R is already, that is the data element and the signal element. So I will explain with one sample problem, right? Very important problem. It is a signal is carrying the data in which one of the data element is encoded as the one signal element. So what is the value of R? 1, because one data element is encoded as one signal element. So the value is R equal to 1 for this diagram. One data element per the one signal element. So the value of R equal to 1. So the R equal to 1. Next here, if the bit rate is 100 kbps, what is the average value of the baud rate? That is a signal rate. And one more thing here, if C is between 0 and 1, the corresponding C value is 0 and 1. So 0 and 1, how to calculate the corresponding C value? That will be 1 by 2. Between the 0 and 1 means that is 1 by 2. So it's an indirect information here. So you have to calculate the S value, that is a baud rate or the signal rate, by the, what is the formula here? C into N into 1 by R. So already the R value is here. Already the R value is here. So the C value is 1 by 2. So the N value here, the baud rate, C equal to N into 1 by R, 1 by 2. This is the N value. So this is the N value 100. Then why it is like 0, 0, 0, 0, 0. So the corresponding kbps is converted into BBPS. Kilobits is converted into bits per second. So it's into 1000. So the corresponding value is 1 lakh. So 1 divided by 2 because the C value, and this is a N value. So 1 divided by 1. That is the R value. So the final signal rate is 50,000. 50,000 is, you can convert into kilo, right? So the K baud rate, that is a signal rate of 50. So this is a simple problem to find the signal rate. Here, to find the corresponding signal rate. Okay, fine. So we will see the common characteristics of the various line coding schemes. Common characteristics of various line coding schemes. Okay. So the common characteristics means here's the baseline rendering and the DC component and self-synchronization, then built-in error detection, then immunity to noise and interface complexity. Then so these are the base of the lines. Here the characteristics of the lines here. So the first one we will see one by one. So the baseline. Okay, so consideration for the choosing a good signal element are referred to as a line encoding. Because the good signal element means that is based on the line encoding only. Okay, fine. So the baseline rendering means here receiver calculates a running average of the received signal power. Received signal power. So here the incoming signal power is evaluated. The corresponding incoming signal, right? In the incoming signal is evaluated against this the baseline, against this baseline to determine the value of the data element. So based on the incoming signal power, I can calculate the value of the data element. That is the first thing, based on the baseline rendering. So next one, if the incoming signal does not vary over the long period of time, so if nothing change between the signal means the corresponding signal may be in the error. That is a cause of error detection or error in the signal or the incoming data elements. Direction of the incoming data elements. That is the second one advantage of to use the baseline rendering. It's check the signal. That's all. Very, very simple. It checks the signal from the source and destination, whether it is vary or it properly encoded, and it is the data element is equal to the signal element. This only. This is a job of baseline rendering, and the good line encoding scheme will prevent the long runs of fixed amplitude. Yeah, so that is another one point to the baseline rendering method. So there's the next one here, the DC component. So what is a DC component? So when the voltage level in the digital signal is constant, the corresponding when the voltage level in the digital signal is constant for the while, so the corresponding the spectrum creates a very low frequency. The result of Fourier analysis, very low frequency. That is a DC component. So that the frequency is based on the voltage. You have to understand that it creates a very low frequency when it is the voltage level is in the digital signal. Okay, the next one, these frequencies around 0 called the DC component, the direct current component. So for the problem is here, the system that cannot pass the low frequency, or system cannot use the electrical coupling via the transformer. So if the DC component receives the extra energy or more power, it's completely useless, because we need the base or the equal DC power to transmit the data signal or the corresponding signal element or the data element. So with the same frequency will be maintained in the entire transmission. So that is a component of DC, right? So the extra energy is completely useless. Next, here the self-synchronization method. So what happened in the self-synchronization? Synchronization means you know very well. So if I log in my Gmail in my system as well as my mobile, so if I send any mail from my system, from my PC, from my desktop, it will automatically reflect in my mobile device. That is a synchronization. If anything happen in the dual systems, it will be equally reflect in the both. So that is called the synchronization. Self-synchronization means it's nothing but it's the same way. The signal will be reflect or the synchronization automatically to transmit the data. So to correctly interrupt the signals received from the sender and receiver, it check whether it is a sender and receiver receives the same data or not. That is based on the self-synchronization method. So the receiver bit intervals must correspond exactly to the sender bit intervals. So based on the bit intervals, if the receiver clock is faster than lower, here the receiver clock is faster than royal. Seriya. So if the receiver clock is faster or slower, the bit intervals are not matched and the receiver might misinterpret the signals. So the self-synchronization always check based on the clock. Either the sender clock and the receiver clock is received the same interval between the bit transmission. If it is equal, the data will be transmit perfectly. We can ensure the data can receive perfectly. Okay, so the next one after that self synchronization, here that is an effect of lack of synchronization. Already I told the sender clock and the receiver clock should reflect the same bit interval. If it is not, some of the loss of signal or loss of data will be happen. So error will be in the between the sender and receiver. So if it is happen, effect of lack of synchronization. So the diagram explained that. So A send the data. So you see the signal rate here. What is the ratio of the first diagram? Anyone? What is the ratio of the first diagram or value? What is the R value? Anyone? Yeah, anyone can answer. What is the R value in the first diagram? Or you can text in the chat box. You just calculate the data element and the signal element. Data element divided by signal element is the R value. So what is the data element here? Are you listening? What is the data element here? What is the signal element here in the first diagram? So here the first diagram corresponding the data element is 1 and the signal element is also 1. So 1 by 1 the R value equal to 1. But in the receiver side the signal is divided into 2. Right? So divided into 2, the corresponding data element is also divided into 2. So 1, 1. So the corresponding R value is differed. So by this calculation, we can understand the corresponding original signal will not received in the receiver side. So this is a lack of synchronization method. So a lack of synchronization digital signals includes the timing information that the data being transferred. Why it is? Because this can be achieved if there are corresponding transition in the signal that alert the receiver to beginning and the middle and the end. So it's continuously watching what is the ratio of beginning stage and middle stage and the end stage. It should be equal to the receiver side also. If it is not, some of the lack of synchronization is there. So the data will be is not equal from the receiver side or the source and the destination. So another one here, the terminology built-in error detection. Sir, what is built-in? Built-in means already fixed. It's automatic, right? So the built-in error detection is used to detect the error while the data is transmitted from source to destination. So it is a capability to detect some of or all the errors that occurred during the transmission. Sir, how it is detected? So some codes are constructed such as such that when an error occurs, it is automatically detected. Right? Some of the code or the medium is there. For example, a particular signal transition is not part of the code. When it is acquired, the receiver will know that the symbol error or the has acquired. So it's continuously check the signal codes, whether it is equal or not. When it is the unwanted code is acquired, so the receiver can identify the corresponding symbol error as acquired. So this is called the use of built-in error detection method. Okay. So the immunity to noise and the interference. Here the immunity to noise and interference means nothing but so immunity means here the noise interference is reduce the noise. The line encoding techniques to make the transmit the signal that with the immunity is noise and interference method. So this means the signal cannot be corrupted, and also it will be stronger than error detection. If it is not corrupted, means the actual data will be sent to the receiver. Very simple. Then the last Cat6 is a complexity. So the complexity is the most robust and that is the code here, the more complex than implement to the price of often paid. That is based on the baud rate or required the bandwidth. Complexity means based on the baud rate, that is signal rate with the bandwidth. So the ratio should be equal with the baud rate order, that is a signal rate, and the bandwidth corresponding the data rate. So this is a method of we have to price or the corresponding cost of effective. So the cost of the value should be normal in the complexity method of data transmission. So these are the Cat6 of the corresponding signal. Okay, see here from where is that? So this is a baseline rendering and DC component self synchronization. Built-in error detection. Here the built-in error detection. Then there is a noise, immunity to noise and interference. Last one is the complexity.